So I've already mentioned anti-aromatic compounds, and we've said that anti-aromatic compounds fulfills the first criteria of aromaticity, but have an even number of pi electrons. So they are planar, they all have empty p orbitals, or they all have, every atom in the ring has a p orbital. It is a ring. It fulfills all the requirements of aromaticity except for the number of pairs of electrons. So there's a typo here, even number of pairs of pi electrons. And the stability of molecules is that aromatic compounds are the most stable, and then cyclic compounds with localized electrons, so those are non-planar, and then anti-aromatic compounds. So anti-aromatic compounds are not very stable. So we go from not very stable to stable to very stable. All right. And interestingly enough, it doesn't just have to be a ring of carbon atoms. It can be a ring with heteroatoms as a member of the ring. And so these rings that we've shown here are heterocyclic compounds that are aromatic. And the thing to know about heterocyclic compounds that are aromatic is that if there is a pi bond to a heteroatom, meaning any atom other than carbon or hydrogen, with a lone pair, the lone pair is not part of the pi network. Example, pyridine. So pyridine has a heteroatom nitrogen that is in a pi bond. And so the lone pair on the nitrogen does not count as part of the pi system. So there are only 3 pairs in the pi network, and it is aromatic. The other thing to note about heteroatoms in aromatic rings is that because the p orbitals are always perpendicular to one another, each heteroatom only one electron pair of a ring heteroatom can be counted for determining aromaticity. because pairs are in p orbitals or sp orbitals, sp2, well, let's just forget about the sp2 part. P orbitals which are perpendicular. And in order to have pi aromaticity, they must be parallel. So we're going to review that further, but just for an example, and since we can only count one pair of each heteroatom towards ring aromaticity, for furan would have 1, 2, 3 electron pairs, and it would be aromatic because that is an odd number. And also thiophene would have 1, 2, 3 electron pairs and be aromatic, since we can only count one pair of the heteroatoms, oxygen or sulfur, towards ring aromaticity. Okay, so we had a little practice quiz. We have some questions here that you should be able to answer. This is a practice for the conjugated diene and what the final towards the conjugated diene of the reaction at the top. So I'll read the questions to you and then I'll let you guys work on these on your own. And this will not be something that you have to turn in, but would be good practice. So we have our question. We have this 1-methyl 1,3 pentadiene, and it's reacting with HBr. So we say, draw the intermediate cation and its resonance pair. So draw the intermediate cation for the reactant and the resonance pair. So this is the cation after hydrogen adds. Then, secondly, draw the 1,2 and 1,4 products. Then tell me which is more stable. Which is the more stable thermodynamic alkene product? Is it the 1,2 product or the 1,4 product? The answers are on the next slide, so try to go through it yourself before you look at the answers. Okay, orbital structure of pyridine. So we were talking about how pyridine is counted towards the pi network and a lone pair is not counted towards the pi network because the heteroatom has a pi bond. So if the heteroatom has a pi bond, the lone pair does not count towards the pi network or towards aromaticity, towards determining aromaticity. And the physical reason for this is that the lone pair will be perpendicular to the pi plane. So it would not be parallel, and in order to be part of the pi or aromatic system, it must be perpendicular. So because it must be parallel, wow, okay. In order to be part of the aromatic system, the lone pair would have to be parallel, but it's not. It's perpendicular, so therefore it is not part of the aromatic system. Only pairs that are parallel are part of aromatic system. So all of the purple p orbitals are parallel. But the nitrogen lone pair is perpendicular, so it does not count as part of the aromatic system. And when we're counting how many electrons are in the aromatic system, we do not count the lone pair of pyridine. So here we have the orbital structures of pyrrole and of furan. So for the pyrrole, which has only one lone pair, recall that I said that we can only count one lone pair of a heteroatom towards an aromatic network. And since this heteroatom does not have a pi bond and it does have a lone pair, it has only one lone pair, we can count that lone pair as part of the aromatic network, so that our total number of aromatic electrons is 6. 6 electrons gives us 3 pairs, which is aromatic. And for furan, you can see that the p orbital is perpendicular to the sp2 orbital of the second electron pair, and that the p orbital containing the lone pair, the purple p orbital, is perpendicular to the other electrons, or is parallel to the other electrons in the pi network. So that one pair of the heteroatom is parallel and counts towards the network. Aromaticity. And one pair is aromatic and does not count towards aromaticity. Resonance contributors for pyrrole and furan can be drawn, showing the lone pair being distributed across the pi network. And the resonance contributors are important factors in determining aromaticity. If you cannot draw resonance contributors, then the molecule could not possibly be aromatic. Benzene, pyridine, and pyrrole are all aromatic but have different electronegativities. The aromatic ring of pyridine is less electron dense because of the lone pair on nitrogen. The nitrogen is very electronegative and it withdraws the electron density of the ring towards itself. The aromatic ring of pyrrole is more electron dense because in this case, the lone pair of the nitrogen is being donated to the ring in order to achieve aromaticity. So in pyridine, the nitrogen lone pair is not part of the ring pi network and is withdrawing electron density to the nitrogen. In pyrrole, the nitrogen's electron pair is required to make the molecule aromatic, and so the electrons are donating into the ring. And for benzene, you can see the normal aromaticity of a benzene ring with only carbon atoms. The normal electronegativity of a benzene ring with only carbon atoms. The most electron-dense part is the pi electrons. More examples of aromatic heterocyclic compounds. So we are going to go through and highlight or circle for each molecule each pair that counts towards the pi network, applying our rules. If a heteroatom has a pi bond, the pi bond counts towards aromaticity, but the lone pair does not. So quinoline has a pi bond to nitrogen, and so the pi bond counts, but the lone pair does not. If we circle all the carbon-carbon pi bonds as well, then we have a total number of 5 electron pairs, which is an odd number, and so quinoline is confirmed as aromatic. For indole, the nitrogen does not have a pi bond, and for every heteroatom that does not have a pi bond to itself, 1 electron pair of the heteroatom can be counted towards the pi network. So if we circle the 1 lone pair on the nitrogen and all of the carbon-carbon pi bonds, the total number of pairs in the pi network is 5. 5 electron pairs, an odd number of pairs, it is aromatic. For imidazole, 1 nitrogen has a pi bond, so we count the pi bond but not the lone pair. The other nitrogen has a lone pair and no pi bond, so we count the lone pair. We also count the carbon-carbon pi bond, so we have a total of 3 electron pairs and the molecule is aromatic. Purine and pyrimidine are DNA bases, or the bases of DNA are the basis of DNA bases. 3 of the nitrogens have pi bonds for purine. So for those 3 nitrogens, we count the pi bond and ignore the nitrogen's lone pair. We also count the carbon-carbon pi bond, and we count the lone pair of the nitrogen that does not have a pi bond. So the total number of electron pairs for purine is 5, and it is aromatic. For pyrimidine, both nitrogens have pi bonds, and so we ignore the nitrogen's lone pair and we circle only the pi bonds. We also circle the carbon-carbon pi bond, and so the total number of pairs is 3 electron pairs, and it is aromatic. We are not going to work on how benzene reacts until we get to Chapter 18 in the second semester of organic chemistry. We do need to look into delocalized electrons and their effect on pKa, and this will be the next topic for this chapter. I'll start this on the next video.